So let's talk about how to make a Hayworth structure. A Hayworth structure is what you see down here, in that you've got a sugar that's represented as a full circle or a ring, like of different atoms, right? So in there, that's what we're trying to make. And what we've been talking about in Fisher projections, we can convert to those Hayworth projections. So we take our Fisher structure, as you see right here, and you go, wah, boom, and you turn it over. So I want you to fully turn this guy that way. See how we're doing that? And when you do, what you find is that the OH that was on that second carbon up here is now on the bottom. And the OH that's on this carbon right here is now on the bottom. And the OH that was up here is now up top. And then the OH that we have right here is now on the bottom. Now, the one that I have highlighted in yellow, he reaches back and actually he attacks. I have it drawn this way, but in truth, what he's doing is he's coming all the way back here and saying, I want you, this carbon right here. And so that OH, what it ends up doing is it kicks out this bond from that oxygen. The hydrogen right here ends up going along with this OH. And that, by the way, is this guy. So this hydrogen came from this guy, but this oxygen right here came from right there, that C-double-O bond. So when he attacks and he reaches back and attacks, then this would be carbon number 1. So if I call this carbon number 1, 2, 3, 4, 5, and 6. On my Hayworth structure, I've got 1, 2, 3, 4, 5, and 6. And just to make sure that you all see where those carbons are, because this does look a little bit different. So what ends up happening is this OH reaches back and he wants to connect with this first carbon right here. And so the oxygen that's right there is this guy. That's where he comes from. Okay? So if that's where he comes from, sorry, I've got too much stuff here. If that's where he comes from, he's reaching back and grabbing where that first carbon is. And he basically just expands and gives his hydrogen to this guy over here. And again, that's where this OH comes from. Now, notice that the same way we could say the OH positions in the Fisher projection just basically shifted when we made that 90-degree turn. We can also say this OH on carbon 2, guess what? Here's carbon 2. He's still pointed down. And this OH on carbon 3, he's still pointed down. OH on number 4, hey, guess what? He's up here. And then the fact that the OH down below is represented there as going down, that's actually what makes it D. And that's the reason why this guy sticks up. So I guess I should put that in yellow there, right? So that's why he sticks up. Now, in the notes, I've color-coded this for you down here in a more simple version. So you should read through this and make sure that you're understanding where things come from, okay? But essentially what's happening here is that a sugar is going from a Fisher projection to a Hayworth projection. It's going from an unconnected entity to reaching down and touching its own toes. And when it does that, it makes a circle or a loop. And that's what's happening, is that these structures can make these rings. And that's how we're going to look at most carbohydrates. But the reality is that these two structures are in equilibrium with each other. Translation. We get a little bit of it that's not touching its own toes and making that ring. but most of it stays in the ring formation, okay? So when that oxygen reaches over to that C-double-O bond to kind of make that touch its own toes, right? He's the one that comes back and reaches over to the C-double-O bond. It can go one of two directions. Either you could go forward and touch your toes, or if you're, talented enough, you could go backwards and touch your toes. That's just a demonstration of what ends up happening here on the first carbon where that C-double-O bond was. So in reality, you can end up having that OH go down, or it can come up. It's just a result of which direction you go to touch your toes, okay? That's what makes the ring. So if that OH on the first carbon goes down, we call that alpha. And if the OH is going up, we call that beta. And here's how I remember that. Apples fall from trees, and that's where the alpha comes from. And balloons rise up, and that's where beta comes from. It's totally not where they come from, but it's an easier way to remember it. Okay. So you can practice this with a variety of different types of molecules. I've listed here for you what alpha D galactose and beta D galactose look like. Notice I'm only using the D's. But again, alpha is when OH goes down because apples fall. And beta is when OH goes up because balloons rise. And you should notice that we're again using this first carbon right here. And we do tend to write it like this in Hayworth projection, where the carbon number 1's on the far right side, or you can look at it to the right of where that oxygen is. And that way you can find it pretty quickly. I gave you another example here of what it looks like for a Fisher projection to go into a Hayworth projection when we're talking about fructose. Because fructose, remember, is a ketose and it does weird things. So in this case, we have 1, 2, 3, 4, 5, 6 carbons, but the OH that's on this last chiral carbon comes over and attacks here, and that means that you actually only have a 5-membered ring. So let me count that for you. We've got 1, 2, 3, 4, 5, 6 carbons. And so see how this oxygen right here ends up being this one right here. So they look a little funny when they're fructose because they're 5-membered rings instead of 6. And just like we did last time, let me point out the fact that alpha has the OH going down. Now, it's not carbon number 1, but it's still the carbon that's to the right of where that oxygen is. As long as you've got it in this order, I should say. And here the OH is going up, and so we still call that beta. Just realize that the CH2OH is going to go in the other direction. Okay, there's one last thing I want to point out. When you do a reaction, there's sometimes different things that indicate change has taken place. Well, when you use something called Benedict's reagent, we can take what's known as a reducing sugar and put it in the presence of Benedict's reagent. And Benedict's reagent originally is this nice pretty blue color, and that is due to the copper that is in it. But if it's in the presence of a reducing sugar, it's going to turn a nice brick red, and it's pretty distinct. And so that's what ends up happening here. So Benedict's reagent will work with a reducing sugar that's basically in its Fisher projection form. So it has a C double bond to O, and the next carbon over has an OH. And so this is just a reaction that can happen that allows us to identify sometimes if you have something like sugar in your urine or something to that degree. Okay, good luck you all. I know Hayworth projections are challenging, but we're going to use them, and I think you're probably going to get more used to them over time. Thank you.